Theorem 1.4, limit theorems on radical functions. So the limit of the nth root of x as x approaches a is equal to the nth root of a if n is odd. But when n is even, the limit of the nth root of x as x approaches a is equal to n of the nth root of a if and only if a is greater than or equal to 0. And I think you understand the reason why this is how it should be when n is even. So our definition of the nth root of a real number is that the nth root of a is equal to b if and only if, if and only if b raised to n is equal to a. And if n is even, if n is even, you know that a cannot be negative. A can be positive or it can be equal to 0, but it can never be negative. And so that is the reason for this restriction, When n is even, the nth root of x as x approaches a is equal to the nth root of a if and only if a is greater than or equal to 0. So the generalization of this theorem is the limit of the nth root of f of x as x approaches a is equal to this. But when n is even, the nth root of f of x as x approaches a is equal to this, the nth root of the limit of our function as x approaches a if and only if this one is greater than or equal to 0, or the limit of this one is greater than or equal to 0. Let us evaluate the limit of the square root of 5x cubed minus 110. It is equal to 5. How about this one? The limit of the square root of 1 minus x times x plus 4 as x approaches 4. So this one does not exist because after evaluating the limit of this function as x approaches 4, we found out that it is equal to negative 24. And this one is a square root. So the index of our square root is even. Conclusion, the limit of this function does not exist. Find the limit of the cube root of 2x cubed minus 3x squared minus 8 as x approaches 2. So it is equal to the cube root of negative 4. And it is just fine if our radicand is negative because this is cube root and is not even. Given a binomial a minus b, its conjugate is a plus b, and a minus b times a plus b is equal to a squared minus b squared. So this is just the result of your multiplication, or maybe you can still recall that this is part of your special product. And so the reason why I am introducing the notion of the conjugate is because this is going to be very helpful when we meet indeterminate forms in radical functions, in evaluating the limit of radical functions. So for example, we have this function 1 over square root of x minus 1. If you want to produce a function that is equivalent to this, but the denominator does not contain a radical function, what you can do is, you can do this. You can multiply this function by this one. So this one is just equal to 1. And by multiplying this to our function, we are not changing our function. But the good result of this is we produce a function, an equivalent function where the denominator does not contain a radical function. Okay, just in case you still cannot see why our denominator became this way, what you can do is you can just get the product of the square root of x minus 1 times the square root of x plus 1. So this one times that is just equal to x. Square root of x times 1 is square root of x. So this one is negative square root of x, and this one is negative 1. So again, the conjugate is going to help you when you are working with indeterminate forms. But this one will produce an expression such as this when what you have in your denominator is a radical function, which is a square root. You know, when I was a student, I was trying to force the conjugate to work on functions such as this. Okay, so take a look at this. This is the cube root of x minus 1. And so the conjugate of this is still the cube root of x plus 1. Okay? But let us see, will this succeed in removing a radical function in the denominator? Let us see. 1 times this is just cube root of x plus 1. Okay? So let us try to get the product of that one. The cube root of x times the cube root of x is equal to the cube root of x squared. Okay? This one times that is cube root of x, and then negative 1 times this is equal to negative cube root of x. Negative 1 times 1 is negative 1. And so what we have here is the cube root of x squared minus 1. So multiplying the denominator by its conjugate does not remove the radical function in your denominator. And you will see what I am talking about when we go to indeterminate forms.